Our whole electrified future, the car you drive, the grid that lights up your home, it all comes down to batteries. But what if the key ingredient in today's best batteries has a pretty dark secret? Well, in this explainer, we're going to dive into the massive global race to build a better, cleaner, cobalt-free battery.
I mean, really think about that. This huge push for green energy is one of the most important things we're doing. But right at the center of it is this one material, cobalt, that is just full of problems. It's a massive challenge for the very future we're all trying to build.
So here's what we're going to cover. First, we'll get into exactly what's wrong with cobalt. Then we'll introduce the new battery chemistries that are ready to take its place. We're going to look at a really cool lab breakthrough that made them possible, check out the global race to get them to market, and finally, ask the big question: can we actually recycle them?
Okay, so what is the big deal with cobalt anyway? For years, it's been the magic ingredient, right? The thing that gives lithium-ion batteries their stability and long life. But all that performance, it comes at a price, and that price is getting steeper all the time.
The biggest things pushing us away are cost and just plain uncertainty. Cobalt is expensive, and its supply chain is, well, it's shaky. That alone has sent researchers all over the world scrambling for an alternative. But then you add in the really serious environmental and ethical problems with how it's mined, and yeah, the need for a change becomes incredibly clear.
And that pressure is really sparking some serious innovation. We're now seeing two major cobalt-free chemistries coming out of the lab, and they're becoming the top contenders to power pretty much everything.
Okay, so on one side, we've got LMFP, or lithium manganese iron phosphate. The easiest way to think about it is like the classic, super safe LFP battery, but on steroids. It gives you up to 20% more energy, and it does it without any cobalt or nickel. Then on the other side, you've got the powerhouse, LMNO, lithium nickel manganese oxide. This one is all about high voltage. We're talking close to 5 volts, which makes it an amazing and affordable choice when you need a serious amount of power.
But, and this is a big but, getting that high-voltage LNMO battery to actually work was a huge scientific headache. We're going to zoom in on how scientists finally cracked the code because it is a fantastic story of solving problems at the atomic level.
So the secret was to build it as an all-solid-state battery. Now, what does that even mean? Well, basically, you get rid of the flammable liquid that's inside a normal battery and replace it with a solid material, a solid-state electrolyte, or SSE. It's way safer and it has the potential for a lot more power. But there was a catch.
And this slide just shows the problem so perfectly. At first, the scientists used a pretty standard electrolyte. You see it there on the left. But it was like a bad roommate. It just did not get along with the LNMO cathode. It created this wall, that red barrier, that basically just choked the flow of energy. So they swapped it for a different one on the right, and the interface looks clean. Problem solved, right? Well, not so fast.
And this is what that bad roommate situation looks like up close. I mean, wow. Those red arrows are pointing to actual physical cracks forming between the particles. This wasn't just a small chemical issue. The battery was literally tearing itself apart before it could even get through one charge cycle.
So even with the better, more compatible electrolyte, another problem popped up. As soon as the battery charged up to those really high voltages, where all the LNMO's power is hiding, the electrolyte itself just couldn't handle the stress. It started to break down, to oxidize. The battery was essentially eating itself alive.
The solution they came up with was just so clever. They figured out how to wrap an incredibly thin protective shield around each LNMO particle. We are talking just 10 to 20 nanometers thick. That is thousands of times thinner than a human hair. This tiny little suit of atomic armor was the key to the whole thing.
And the results? They were just incredible. Take a look at this. The uncoated battery could barely deliver any power at all, but with that nanoscale coating, boom! The discharge capacity shot up by nearly 300%. That protective shield didn't just help a little. It unlocked the battery's absolute true potential.
Of course, a breakthrough this massive doesn't just stay in a lab for long, right? No way. This kind of discovery kicks off an intense worldwide race to patent this stuff, produce it, and get it into the market.
And the scale of this race is just mind-boggling. Just for that other cobalt-free chemistry, LMFP, there are already more than 7,800 patent families filed. That's not just a trend, that is a tidal wave of R&D money and brain power pouring into this technology.
And things are only speeding up.
Since 2023 alone, over 410 new companies have jumped into the game and started filing their own patents. This just shows you how incredibly competitive this space has become in a really short time.
So, where is all this innovation happening? Well, this chart makes it pretty clear. A staggering 80% of all the new companies that have entered this race since 2023 are from China. This really highlights a huge strategic push to lead the next generation of battery technology.
But hang on, there is one final, absolutely crucial piece to this puzzle. If these new batteries are really going to give us a sustainable future, it's not enough to just solve the cobalt problem. We also have to solve the end-of-life problem.
This is the big question, right? This will decide if we're just trading one environmental problem for another one. I mean, what's the point of a cleaner battery if millions of tons of them just end up in landfills? The good news is, researchers are already on it.
And there's already a clear plan to get all the valuable stuff back. It's a multi-step process that uses liquids to pull out the metals. It starts with high heat treatment, then they separate the parts mechanically, they use a leaching process to dissolve the metals, and finally, they pull out each one to be used again.
So, does it work? Oh yeah, it works really, really well. This process has hit peak recovery rates of up to 90% for key materials like nickel, manganese, and lithium. This proves that these new cobalt-free batteries aren't just high-performing, they are highly recyclable. We can get that raw material back and build the next generation of batteries.
Which brings us right back to the beginning. When you put it all together, we're talking chemistries that are cheaper, safer, and sourced more ethically, breakthroughs that unlock their full power, and a real, clear path to recycling them. Are we finally looking at the batteries that can power a truly sustainable world?